Every single time you shop online, check your email, or just browse the web, there's this secret language working in the background, keeping everything you do safe. That language is called cryptography, and it's pretty much the hidden foundation of all the trust we place in the digital world. Yeah, we all see that little padlock icon and the S in HTTPS in our browsers every day. But have you ever really stopped to think about what it's actually doing? Well, that S stands for secure. And in this explainer, we're going to pull back the curtain and show you exactly how all that security works. All right, so let's start at the very beginning with a problem that's, as old as writing itself. How do you send a message so that only the person you want to read it can actually read it? This is the core secret message problem, and cracking it is the first step on our whole journey. Okay, so everything starts with your original message. In the world of cryptography, we call this plain text. It's just what it sounds like, plain, simple, readable text. It could be an email, your password, any information that's just sitting out in the open, totally vulnerable. So to protect that plain text, we have to perform encryption. Now, this is just a fancy word for the process of scrambling it all up. You take a secret key and a special mathematical formula, an algorithm, and you basically lock that readable message in a digital safe. And what comes out on the other side? That's what we call ciphertext. To anybody snooping around, it just looks like a bunch of random, meaningless gibberish. But we know it's our secret message, all locked up and ready to be sent safely. And then, finally, once the message gets where it's going, the person on the other end uses the correct key to perform decryption. They just reverse the whole process, turning that scrambled nonsense back into the original plaintext. And just like that, the secret has been delivered successfully. So we have a way to lock and unlock our messages. And the most straightforward way to do this leads us to our first major system of cryptography. But as you're about to see, it also comes with one very big problem. The easiest approach is something called symmetric cryptography. And honestly, it works exactly like your house key. You use the very same key to lock your door when you leave, and you use that exact same key to unlock it when you get home. One key does both jobs. So the process is super direct. The sender locks the message with a secret key, they send the scrambled message, and then the receiver uses an identical copy of that exact same secret key to unlock it. Simple and really effective. And there's a reason this method is so popular. It is incredibly fast and efficient. I mean, blazing fast. This speed is why modern algorithms like AES and Cha-Cha-20 are the true workhorses of the internet, encrypting massive amounts of data every single second. But, and here it is, here's the huge fundamental flaw. If you and the receiver both need the exact same secret key, how do you get it to them safely? You can't just email it to them, an eavesdropper could just grab it. This is the classic key distribution problem, and it's a real headache. So, to solve that problem, cryptographers came up with this incredibly clever and elegant solution, a totally different way of thinking about keys. I like to call it the public mailbox solution. So instead of trying to figure out a clever way to share a secret, this new method asks a completely different question. What if we could build a system where you didn't even need to share a secret key to begin with? And this is the absolute genius of asymmetric cryptography. Instead of one key, everyone gets a pair of keys that are mathematically linked together. They're like a matched set, two sides of the same coin. Whatever one key locks, only its partner key can unlock. Let's go back to that mailbox analogy, because it explains this perfectly. Your public key is like the mail slot on your mailbox. You can give that address to anyone in the world. They can use it to encrypt a message and drop it in the slot. But, and this is the critical part, only you hold the private key. That's the one and only physical key that can actually open the mailbox and read what's inside. That private key never ever leaves your sight. Okay, so this public key system is fantastic for talking one-on-one. But how do we make that work for the entire internet? How do we build a global system of trust so you can communicate securely with absolutely anyone, anywhere in the world? Well, this creates a brand new challenge. Imagine you find a public key online that claims it belongs to your bank. How can you be 100% sure it's legitimate? How do you know a hacker hasn't just swapped in their own public key, tricking you into sending them your password? The answer is something called Public Key Infrastructure, or PKI. It's basically a whole system built on these trusted third parties, called certificate authorities, or CAs for short. Think of them as the official notaries of the internet. Their entire job is to verify that you are who you say you are. And they do this by issuing what's called a digital certificate, which is really just like a digital passport. It has all the key info, the website's name, its public key, and most importantly, a digital signature from that trusted certificate authority. Your browser can instantly check that signature to confirm that the certificate is legit and that you're really talking to your bank and not some imposter. So it sounds like we've got these secure systems all figured out, but the story doesn't stop there. Cryptography isn't a static thing, it's a constant arms race. It's a never-ending battle between the people building the locks and the people trying to pick them. The most basic way to try and break a lock is just to smash it with a hammer. In the crypto world, that hammer is a brute force attack. And it's exactly what it sounds like. A computer literally just starts trying every single possible key, one by one, until it hopefully stumbles on the one that works.
So how do we defend against that? Well, it's pretty simple. You just make the number of possible keys so unimaginably enormous that it's impossible to guess. With something like a modern AES 256 key, it would take the fastest supercomputers on Earth billions of years to try every combination. And on top of that, we add other defenses like rate limiting and account lockouts to stop attackers from just guessing millions of times a second.
And this brings us right back to where we started. This is the big secret. Modern internet security doesn't choose just one system, it uses both. First, your browser uses that slower but super secure asymmetric crypto to check the site's digital certificate and safely agree on a brand new temporary secret key. Then, for the rest of your visit, it switches to the lightning-fast symmetric crypto, using that new key to encrypt all your data. This hybrid approach, this elegant, best-of-both-worlds handshake, is a protocol called TLS, and that is the S in HTTPS. So we've built this incredible system of digital trust, one that protects us every single day. But, like we said, the battle never ends. Today's encryption is designed to defeat today's computers, which leaves us with one final and pretty critical question. What happens when tomorrow's technology finally arrives? A new kind of computing so powerful that it can shatter everything we've built.